Okay, let's get ready. We're for this next session, which we're a minute ahead, but that's okay. For this next session, we're gonna do the simulations and then do the inversion. So it's we're compressing a lot in 20 minutes. I hope the idea comes across, and of course, to really get this going, we're gonna need a lot of. You're gonna need to put a lot of on your side when you try to use it in your cases. But again, we're always open for questions, for emails, and video chat. That's okay. So what we mean by simulations. Simulations in UTEP Wells, the ones that I'm going to talk about right now are the most straightforward simulations that you can have. In a few words, suppose that you have a resistivity model where you just have resistivity values, this blocky log for resistivity in a segment, and you want to turn it into the tool response. You want to see what is the tool response for that. You open the resistivity logging simulator, which is going to look something like this, and you get, sorry, you get a curve. You get the tool response. This is what you're looking for. This is what you're going to compare to the field data. A couple of words of warning. Most simulations, first, every simulation has a tool in resistivity and a variant. The tool is what it sounds like, is the physical tool that is being used. The variant is the program that is modeling that tool. It's going to have a dimension, 1D in this case. There's 1D and 2D. There's only one 3D, I think, for resistivity, but it's way too slow. So we only use 1D and 2D really. And then you have a number of other options, whether you want it to be anisotropic, where you want to use a little more advanced cases, where you want to use relative electrical permittivity, relative magnetic permeability, the frequencies that you want to simulate, in this case 400 kilohertz or 2 megahertz, and then the log set where you're going to output the result. And many of these programs are going to run, most of them are going to run external programs, not MATLAB based, that pop up a command window. It runs the program in that command window, and then it closes, and UTEP Wells retrieves the information and puts it back in there. Sometimes, if there's problems, or if you're related to the developer, or you're working with the vendor, in many of these cases, the variant was developed by a service company, and if you're talking to them, you may want to see the results directly on the command. If you, in that case, you do not close the command window on completion, and you see a little more of the results. Now, regarding the dimension, the 1D in most cases is going to assume no invasion. So it's just along this dimension. However, it can handle well trajectories, or varying well trajectories and bed dips. They can be changing. So if you're interested in seeing deviation, you would use a 1D. 2D, on the other hand, it can handle invasion. So if you're interested in invasion, you use a 2D. But beware, because it always assumes that the trajectory is completely straight. So depending on what you're trying to do, use one or the other. If you have a case where the trajectory is not straight, like in most cases, but you run a 2D invasion, that's okay. We're just going to break it into segments and then put them together. Be aware of that also. Same thing happens with 1D. In many cases, it can handle deviation, but constant deviation. So if that happens, we also break it into different segments. We run the external program multiple times and put it back together. All of them assume azimuthal symmetry. 2D actually, 1D doesn't. Okay, now this is also a lot of information, but that's okay. These are all the variants and all the tools that we have available, whether they can consider anisotropy, whether they can consider electric permeability, magnetic permittivity, and dipping. All of them are here. You're going to have this presentation, so you can have them. And this is very easy to infer from the program itself. So let's look at the example that I was showing you. This is what I was showing you. And the simulator, to access the resistivity simulator, you go in here and you get this window. And like I was saying, all the information is easy. Well, in the top, you always have the well that you're working on. Then you have all the tools. It's very easy to go over them. And then all the variants. In this case, for ARC, we have a 1D UT semi-analytical, which is very fast. A 1D UT, I think it's a finite element. Then we have a Schlumberger developed, and we have a 2D mode matching algorithm. And depending on the tool that you're working, you're going to have different options. In this case, you have the models, you have the sampling interval, so on. Then this straight trajectory approximation is going to be when the deep variation is larger than that, we're going to break it into segments, the segments that I was talking about. Now, the main reason why you would do simulations is because you want to test different hypotheses. So if you see, in this case, you can see that there's some separation between the tool response and the actual Earth model. You would allegedly, or not allegedly, but for sure would do better petrophysical analysis if you use the Earth model rather than the tool itself. The further it deviates, the more benefit you're going to have from modeling. Now, an interesting case is also to test different deviations. So I open this window by going here where it says well geometry. You can also do Earth model well geometry. Opens up this window where it shows you the depth of all the bedding planes, the true deep, true azimuth, relative deep, relative azimuth. It's all 0. We're just assuming it's a straight well going down. That's it. Here is where you would apply the trajectory. You can load a survey file, or you can take it from logs, depending on the format that you have. Or in many people, what they do is they just, because they're interested in a small section that can be considered straight, and they want to test the different scenarios, they just say, okay, the inclination in this case, let's say, is 35. You just type that there, and you immediately see that in the view. You see that reflected. You see, well, this is just the starting point for the survey. The well path calculation, what are you going to use? Minimum curvature is pretty standard, but some people use others. And here you see that the true deep is 0, but the relative deep has been modified. By the way, you can modify that here. You can make this a little more interesting. But let's stick to simple. So they're all parallel, but the well is going with a 35-degree deep inclination, which turns into a 35-degree relative dip. And if we run the same simulation, the same resistivity simulation, but for this geometry, you're going to see that, that window popped up, and now you're going to see that the curve is going to be modified slightly. It wasn't all that clear. Let's make it larger so that we see that modification. Now it's very clear. You see it changed significantly from what we had. And in this case, you definitely want to do modeling in a deviation of 60. Just for kicks, let's make it 85 to see in a case where it's really deviated, how much would it look like? So you would very hardly infer an Earth model that looks something like this from this curve. So to the point of deviation, really is a case where you want to do some modeling. I want to see this 35 again and see if it really doesn't. Well, there's a change. It's a very small change, but there is a change. And we know that in general, if it's less than 35, there's is not really. It's not high inclination, so it's not assumed to be a critical problem. But you do see cases like this one where there's enough of a separation that when you turn that into water saturation, that's going to be reflected. So compared to the 0 case, it's a very different interpretation that you're going to give. Okay, so this is one of the cases I wanted to show you. Also, I'm still just focusing on resistivity, and I will only focus on resistivity. Keep in mind that we have very similar simulators for nuclear. I just want to show you where they are. This one is for nuclear simulations. We have Wireline and LWD, the Schlumberger tool, and we have Sonic, which is very, very simple. It only works for straight wells with perfectly perpendicular cases. It's analytical, so it's very fast, but of course it's limited. Even though it's limited, it's a good to have, because shoulder bed effects for Sonic tend to be very large. Now, this is a case that we've worked with in most, pretty much every workshop. You've seen it. If this is not your first class, you've seen it in the past. It's a real case scenario inspired model that we have. I've loaded the gamma ray in here, and here we have the RT90, the resistivity. I have 3 resistivities. I have, let's hide everything, and well, not the boundaries, but let's add them one by one. This is the field log that we have. Then I detected boundaries, and this is what I got. Then we have the Earth model, which of course is blocky. I just populated properties the same way you would do it. Now it's the same way we did it before. And I'm just going to make this larger to make it easier to see. And you can see it's just taking the mean and the max, so it would be your first guess. Not just your first guess, but this is what most people would infer. As if they're doing standard interpretation, this would be what they would infer. And then I have done the simulation for this case using an AIT. This is AIT to the AIT-H. This is another tool, of course. And we have this ideal borehole case. For 2D simulations, we have 3 different scenarios. We have the ideal borehole, which is what most people will use. This is what you can, in most cases, this is what you can compare to what the service company is going to give you. Then we have the variant tool correction, which is what they would give you. So what they would give you, but without correcting for borehole conditions. And then the no correction is the raw data. You can read a little more if you're interested in those cases. We can exchange email if you're even more interested. Now, if you see the simulated log here is not being a perfect match, which means that the resistivity is probably not the resistivity that we're seeing. So the interpretation that we do after this would be wrong. We can modify this by just moving. You can just move the Earth model by dragging and dropping. And if I simulate again, you can see that the match is going to be a little better. Now, maybe I went a little too far here. I can simulate again. To make it a little more quantitative, I can add another plot. I'm getting a little better match. So allegedly, I'm going to get better formation evaluation using these resistivities rather than the ones in the middle of the borehole. Now, I'm going to add another plot, which is going to be a shade plot, just to get this a little more closely. The left curve is going to be RT90 and the right curve is going to be RT90, but the other RT90, I'm going to show some cases I'm undershooting, overshooting. Notice that it also gives you the RMSD, that's root mean square deviation on meters. So this is the number, this is the separation, the root mean square deviation between these two curves. Ideally, if we have a perfect match, it would be 0. It does not happen. But if we get it closer, that would be good. So I can keep doing this manually, and this is what people used to do for a long time, but of course seems like a very tedious task that nobody should do, and that's not what we do nowadays. For these cases, we have the module that we call the MCMC, Markov Chain Monte Carlo, and this is what it looks like. What it's going to do is we're going to decide which property we want to invert for. So let's say resistivity. you can do it by raw class. Let's ignore this for now. You decide which tool. It's by default is set up to the one you're using in the forward simulator. You can get that simulator just by clicking here in settings. And then you decide which curves you're going to match. So here you have all the curves that this tool is going to simulate, and we're going to try to match it to the thin beds, the log set that I loaded that has the same curve. I'm going to say run, and then I'm going to explain what is happening. I'm going to say run, and it's going to start modifying the resistivity to try to match as closely as possible the field log with the simulated log. Now, we do this, we have two methods. We have the Latin hypercube and quasi-Newton. Both of them are in-house developed. Latin hypercube, sorry, quasi-Newton was developed by Tianxi, Carlos, and myself, mostly Tianxi. And what it does is it approximates the separation by using the Jacobian. It assumes there's some slope that it can follow and makes the match. The Latin hypercube, well, makes the match, and not only makes the match, but estimates uncertainties. The Latin hypercube tries to maximize the a priori probability by ad hoc rules, and then generates a Latin hypercube, which, if you are interested in the details, look at the video about the talk for the method. But it generates a set of possibilities around the best possibility found, and that is what you use to generate uncertainties. Both of them are pretty good. If all you're interested in is getting the maximum a posteriori, which means just as close of a match as you can get, you can just do the initial accelerated search. You could say, we always break this into two. If both methods break this into two steps. The first one is just to get as good of a match, and the second one is to calculate uncertainties. The first one is called the initial accelerated search. You can do only that if you're interested in only that. And then there's a certain perturbation that you use, and then it's going to exit after a number of iterations. This is the finish criteria, number of iterations, or if the RMSD is a certain number. Now, notice we have three plots here. We have, in the top, we have the misfit. In the middle, we have the RMSD, which is just mean root square deviation, which is very easy to understand. It's just you get the field log minus the simulated log square, so that they're all positive, add them all together, and then get the square root. That's it. So it's literally root mean square deviation. But in some cases, and very, very closely is going to be followed by the misfit, but the misfit is the same thing, except, so you can see it's target minus simulated squared added. There's no square root in this case, but that's okay. It's not going to change anything because the square root is always growing related to the space. But we're having this noise in the bottom, and this noise is a measurement of the tool. In some cases, it's just a fraction. In some cases, is not a fraction. The cases that we have for noise are absolute. In this case, we're just saying it's a fraction, 0.03. For resistivity, it might be a fraction, but most tools actually do it as fraction plus absolute. So, but this is okay. What we're doing is fine for now. This is something you would see in the tool specifications. It's literally the noise that you expect. And this is what you would do. We have more advanced options for borehole corrections. For noise, we can increase the noise if the caliper is telling you that the numbers are not right. These are advanced options. I'm not going to go into too much detail with them. Anyway, so first we're trying to match it as close as possible, and then we're calculating the uncertainty. So these two are going to follow each other pretty closely. This one you can also see in log scale or linear scale. These two are going to follow each other pretty closely, and the idea is that they decrease. This one looks good. And here we see that the separation between the two of them has decreased significantly from where we were. And we can see that the resistivity values are significantly farther from what you would have assumed at first. Now, at this point where it's out of the accelerated search, it's calculating the mean uncertainty, or it's calculating the uncertainty for every layer. Here in this plot is showing us the mean uncertainty after the number of iterations that it's done. This first part where it dips, at first it's very low, then it grows. It's increasing the number of samples, it's going to grow. Then it drops. This is where it went from accelerated search to out of it. And then it drops, and then it starts growing. And we're going to see it growing as we keep adding samples to the ensemble until at some point it's not going to grow anymore. And if it's not growing anymore, we can safely assume that sorry, I'm adding more people. So if it stops growing, we can safely assume that we have done a good job at calculating the uncertainties. And I say safely, but in this case, it's never completely perfect. You get a good idea, and you may miss something. It's a very complicated problem, but we do a very good job at giving you a result. And the difference between the two methods, between the quasi-Newton and the Latin hypercube, is going to show here. The quasi-Newton is going to be a lot faster to give you an answer, but the answer is going to be a little more constrained. It's going to be a pretty good accurate answer with a small number of iterations. But it's assuming that it's symmetric, meaning that the uncertainty is always going to be symmetric. So it's going to be Gaussian, and you're going to miss some cases. We have a couple of papers coming out understanding this. In general, the confidence intervals are going to be a little smaller with the Latin hypercube, meaning that you're going to be you don't have as much guessing to do. Whatever it gives you, it should be is more accurate, and they tend to be smaller. Now, right now we're at 50 sample points. It's still growing a little, but not really. So I'm just going to stop in here and say, good. We're going to assume that the results that we have are fine. Now, here we can see that the match is much better. It was 23. Now let me see if the RMSD is still pretty high, but that's okay. That's okay. You can see that they are very far from each other. Sorry, they're very close to each other. They're almost on top of each other. The simulated, I'm going to make it a little wider, just so that we see where it is. And it's pretty much on top of the other line. Now we can also see the Earth model. Right now it's this blocky log, and I'm also going to make it a little wider so that we see very clearly where that blocky log is, where the resistivity that we should use for formation evaluation is. And some of the things that we added this year is now we can show, we always were able to show standard deviation, which it assumes symmetric, but I prefer to see confidence interval. To make it comparable to standard deviation, it should be something like 66. But to be very confident, let's make it 95. And you can see, of course, that higher resistivities tend to have higher uncertainties. Not always the case, but in most cases it is. And what this means is that you have 90% confidence that the resistivity is between these two endpoints. And you can also see it as a heat map. You can even hide the line and just see the heat map. Some people will prefer these so that it's not as plotted. You can see the heat map. It shows you where the samples are. If you see more yellow, this is the color map that we're using. So yellow means a lot of samples are there. So if you see yellow, it's high confidence. Here we don't have as much confidence. This one has some higher confidence section, and then some section with lower confidence, but still possible. You can change the transparency if you prefer to see it higher colors, or if you're more focused on that, you may want to reduce the transparency if you want a zero transparency. makes alpha 1. The number of bins, if you want to see higher resolution, you make it 20. It's just not very good resolution, but if you make it too high, also it's not as good. It's up to you to see what you prefer. My experience, something around 60 or 80 is a good number, so that's why that's the default. And then if you prefer other colors, you can change those colors to make it more what you like. So this is what I wanted to show you regarding forward simulations and inversion. If there's any questions, this is a good time. Go for it. Was it clear? Yeah, this is something. People. It's probably one of the main uses of UTEP wells. Probably the main use of UTEP wells, and people have.
Can you expand out to the modeling interval? I want to see if there's a place where I'm surprised that the errors seem to be still kind of large. I wonder if there's a place where it's missing.
Yeah, it might be that. No,
no, it still looks pretty good. I don't know.
Yeah, I don't know. It might be just, I don't know. To be honest, I don't know.
I think you need to add more boundary in 50 below 5040. There is like a peak. You need to add boundary here. I think you will enhance it more.
Yeah, so
yeah, this one,
this area,
yeah,
right?
Yeah.
I think you're right.
Yeah.
I think you're right. Here we should have a boundary. Yeah. And the rest looks okay, no?
Yeah, most of that looks pretty good. That's why I was surprised that it wasn't like closer to 0.
Yeah, but this area for sure could be.
Yeah, you might even need more than just that one because it has it.
Yeah. Now, if we run it again, of course, we're going to lose all the information for the uncertainty, but that's okay. We'll see improvements here, which is really, at the end of the day, that's what we care about. Okay. Well, let's take a 2 minutes break. Or if there are more questions, I'm not even going to leave this time to go to the next step. Just to see if we get, how close do we get here? Well, actually, let's use this time a little more productively. Something else that I wanted to show you is other things that you can do here with a table view. Sorry, with the track display. We have a couple of icons here. One is cross-plot module mode, that if you click here, you can, the icon is going to change, and then you can click anywhere, drag, drop, and it's going to make this selection, takes all the curves that you have here, makes a histogram for each one of them, and makes a cross plot for the combination of them. So it's a very quick way of making cross plots. And you can see how they relate to each other. Of course, with the Earth model, because it's constant values, you see these straight lines. And the Earth model tends to be a little more more specific values. So you see this gap that you wouldn't see with the log, the simulated, but these are the real values that you see. So this could help you make rock classes, and you can this one you can use to make some selections. So I can draw this polygon, and it's going to select these points and tell me where those points are. There. Anyway. Now it's showing me where those points are. So it's the low resistivity. And you can do it that back and forth. So that the MD selection, and you saw all over the place it's selected. So this is an easy way to go back and forth between cross plots and the tracks. And You can clear it here, just that little point. Say bye-bye. We also have a histogram. If you're just interested in the histogram, just select, drag, drop, make a histogram. In this case, is for that gamma ray. All right. Any comments or questions before I go to the next section?